In this very first problem, we have a rectangle which has a length that is 1 centimeter more than twice its width. And we are also given that the area for this rectangle is 36 square centimeters. We're asked here to try to determine what the perimeter for the rectangle is. So if our goal is to find the perimeter of the rectangle, then we need to find what is the total distance around the rectangle, right? So if this is kind of just a sketch of what a rectangle looks like, we're going to need to know what the length and what the width is, because ultimately the perimeter is going to be two lengths added together with two widths, right? Now we don't actually right now know what the length is or the width. We do know that the area is 36 square centimeters, so we know that for a rectangle, that area of a rectangle is the length multiplied with its width to give the area. Then I can actually plug in the number 36 for the area, of course, right? Now, if we want to find the exact length and width, we need to know a little bit more, and what we also have to work off of is that the length itself is 1 centimeter longer than twice its width. So that would mean if you took that width and you twiced it, so you doubled it, and then added one more unit to that, it would be the same as what the length is. So, right, if you double the width and you add one more to it, then that would equal the length, right? So those couple of statements, this one right here in the blue and that one right there in the red, are really useful. So if we can kind of integrate them together with one another, we might be able to solve for either the L or the W. So the red one, you actually have the L isolated on one side, and since L is the same as 2W plus 1, then we could just do some substitution, and we could take this 2W plus 1 that's equal to L and plug it in for then L into that blue equation. So what that would look like then is we would have 36 equals, and I'll have to put this quantity of 2W plus 1, and since it's going to times with W, I'm going to have to put 2W plus 1 in parentheses right there so that that whole quantity multiplies with the W that comes after it, right? So here's our 36 equals the length of 2W plus 1 times the width, right? So now this just involves a variable W, and we should be able to solve for just this value of W. So if we distribute right there, we're going to end up with 2W squared and then plus W, and that's going to be equal to a value of 36 right there. So now we run across a quadratic equation in the variable W that we're going to want to try to solve here. And so anytime we're solving a quadratic equation, whether we're doing it by factoring or completing the square quadratic formula, it's nice to be able to get a 0 on one side of the equation. So we could accomplish that if we get a 0 on this side. And then if we subtract 36 to both sides, we end up getting something like that, right? Okay, so you could try factoring. You could also use quadratic formula since it's always reliable. So why don't we use quadratic formula? So we know that the value of W would be equal to negative of B. So your B value is a 1. So negative of 1 plus or minus the square root of B squared. So 1 squared minus 4AC. So my A value there is a 2, and my C value there is a negative 36. And that's going to be all over 2 times A, where A is 2. Okay, so we'll get negative 1 plus or minus. So inside of that square root, you're going to have 1. And then you do have a negative times a positive times a negative, which will equal a positive. So it'll be plus something. And then if you take 4 times 2 times 36, we end up getting 288. And that's going to be all over 4 then. So just kind of writing this out here, I'm going to write that as the separate fraction, negative 1 over 4, and then plus or minus the square root, adding together 1 and 288, we get 289, and then that's going to be over 4. It does turn out that actually this square root, 289, will come out very nice, because 289 is a perfect square. 17 times 17 gives you 289. So we end up getting then negative 1/4 plus or minus 17/4, okay? All right, so with that, you'll be able to get a couple nice answers out of that. So if you plus these fractions, they already have the common denominator of 4, then negative 1 plus 17 gives you 16/4. And then if you minus, negative 1 minus 17 gives you negative 18/4. They both would reduce kind of nicely. So you would get positive 4 would equal W, or negative 4.5 would equal W. Okay? Now remember that in this situation, we're modeling area, and the W is actually representing the length of the width. So that negative 4.5 wouldn't make sense in this situation, okay? Although it's a solution to the equation, it's not going to make sense because you can't have a negative width, right? So really the 4 for W would be the only thing that makes sense to have a width that's actually 4 feet. So yeah, let's just kind of check to verify that that's going to be right. And then, right, our goal was to find the perimeter of this rectangle. So let's plug in 4 for the width. And then if we wanted to find the length, remember this relationship right there, that the length is 2 widths plus 1. So if our width was 4, 2 times 4 is 8, plus 1 is 9. And so we would get 9 and 4 are the dimensions for that rectangle, right? So ultimately, to kind of answer this question, the perimeter really is just going to be 2 9s plus 2 4s to give you the perimeter, which is the same thing as 18 plus 8, which is then going to give you 26, and the units would be centimeters for the perimeter, right? One other thing that you might want to just kind of think about to verify that this all makes sense too is that when you do have the dimensions 9 and 4, that area of 36 centimeters squared definitely holds, right? Because 9 times 4 does give you that area of 36. Okay? All right, so that kind of finishes up that particular problem right there. So we'll jump to this second example right here. So in the second example right here, we have that a rectangular vegetable garden measures 42 feet in length and 8 feet in width. You want to double the area of the garden. And in order to do so, you'll expand both the length and the width of this garden by an equal distance. We want to determine what the new dimensions of the garden are, right? So our goal is to figure out what the new dimensions, or in other words, what the new length and what the new width would be after we make this garden bigger by doubling the area, right? And the key thing here is that in order to actually double the area, we're going to expand both the length and the width by an equal distance. So what that means is, let's say right here in the red, right, this is our current width, and our current width is 8 feet. And then right here in the blue, this is our current length of this garden, which we know is 42 feet. So what's going to happen is we're expanding both the length and the width by the same distance, right? So I'm going to go outwards more in that direction to expand the width, and outwards more in that direction to expand the length. And ultimately, however far we expand out that direction, and that direction is going to be the same, right? So, for example, if I were to make this 2 feet longer that way, then that would have to be 2 feet longer that way. So it's an equal distance, right? So what will happen then is we're going to get a garden that's bigger, right? Now that's going to be a new rectangle, and we want it such that the area doubles, right? All right. So since we want to expand out an equal distance that far, but we don't really know how far, we might want to represent that with a variable, right? So let's say that we're going to increase the length by x feet. That means that we're going to increase the width by x feet as well, right? So this new rectangle that we have here will now have dimensions where the length will be x added to 42, and the width will be x added to 8, right? And what we want is we want this new larger rectangle that I outlined here in black to have an area that's double of the current garden, right? So really, if I just take the length of 42 plus x for this larger black rectangle, and then I multiply it with the width of this larger black rectangle, then length times width should equal the area of this new garden, right? So currently, our old garden, the 8 by 42 one, would have an area that's equal to 8 times 42, and 8 times 42 is equal to 336. So if we wanted the black rectangle to have an area that's double of that, then double of 336 gives us 672, right? So what our model is really just saying right here, right, is just the new length of our rectangle and the new width of our rectangle multiplied will equal an area that's going to be double of our current rectangle, right? So yeah, now that we've kind of modeled this, this is something we'll be able to solve to find what x is, which is exactly the amount of distance we need to add, right, to both the length and to the width. So there's a little bit of foiling that we can do right here, right? So we can do 42 times 8, which will give you 336. And then 42 times x, which is plus 42x, and then x times 8, which is plus 8x, and then x times x, which is x squared. And that's equal to 672. All right, so we have a quadratic equation. So let's kind of get everything all on one side. How about? So I'm going to write the x squared at the front right there. There's a couple terms right there that are like terms that I can combine. 42 plus 8 is plus 50x. And then finally, let's subtract the 672. So we get a 0 on that side. And subtract 672 right there. That will give us then minus 336, which is equal to 0. All right, so now that we've got this quadratic equation, and then we've got an expression on one side that's in standard form, then we want to try to solve this. So we could, if you could figure out how it factors, if it factors nicely, you could do that. We could maybe complete the square. We could use quadratic formula, whatever you want to use, right? So I'll go ahead and just use quadratic formula, how about, right? So my A is going to be 1, my B is going to be 50, and my C is going to be negative 336. So the value of x here will be equal to negative of b plus or minus the square root of b squared minus 4ac all over 2 times a. Okay. All right, so that plugs it all in, and then we just got to simplify this to find the solutions for x. So we're going to end up with negative 50 plus or minus the square root. If you take 50 squared, you're going to get 2,500. And then if you do 4 times 1 times 336, you end up getting 1344. And you'll end up plussing that because you were taking a negative times a positive times a negative. And that's going to be all over 2 times 1, so over 2. All right, so we're going to get negative 50 over 2 plus or minus the square root of 2,500 plus 1344 will give us 3844. So if you plug in 3844 under square root in your calculator, you'll find you get a nice whole number because 3844 is a perfect square. So we're going to end up with this. That actually is negative 25 because it's negative 50 over 2. And then you get 62 when you square root the 3844. So actually, since the 62 is over 2 and it's divisible by 2, it's actually just a whole number, which is 31. So we end up with this, negative 25 plus or minus 31. So you get a couple nice integers, right? So if you plus negative 25 plus 31 is going to give you an answer of 6. And then if you minus negative 25 minus 31, it's going to give you an answer of negative 66. Okay. All right, so since what x was representing in this situation was the amount of length, right, here to add to both the length and the width, it would only make sense if x were positive, right? So that negative 66 answer that we got for x is not going to make sense. So really only the 6 answer should make sense, right? So we're going to add 6 feet to both the length and to the width. So yeah, to kind of check this out, we're asked for what the new dimensions of the garden would be to answer this question. So the new dimensions would be 42 plus 6, so 48, and then also 8 plus 6, so 14. So the new dimension should be 48 feet by 14 feet, and that should answer the question. And then just to kind of make sure that this also makes sense, right, we were supposed to double the area by adding this equal amount. So if you did have 48 times 14 and you figured out the answer to that, it should give you the new area, which is 672 feet, which we wanted to be double of the original area, right? And when you compare 672 to the original area of 336, it is indeed exactly double. In this last example problem here, we have that a 12 meter by 16 meter lawn space is to have a pedestrian path of equal width installed around it, as is shown in this picture. Due to budget constraints, only 333 square meters of brick is available to use. We want to be able to determine what the greatest possible width for this path is. So, since we're trying to determine what that greatest possible width is, right, then in this picture, where that gray color is, where this pedestrian path is to be constructed, we want to know how long that width is supposed to be, right? And what's really important about this is that when we construct this pedestrian path, the pedestrian path is supposed to be of equal width, right? So that means all the way around it, right, the width of this path is the same all the way. So all of those widths there are just the same number, w, right? Okay, so we want to be able to try to solve for that. Now, that green color that you see in the picture is the lawn space, and we have the dimensions because it's a 12 meter by 16 meter lawn space, right? So we know that from there to there, that's going to be 16 meters across, right? And then also from here to there, that's going to be 12 meters across, okay? All right, so we also know the amount of brick that we're able to use, which is the area of it, so 333 square meters. So what will be really helpful for us here is to understand is that if we actually know the area of all of the brick, and then we actually have the dimensions of the lawn space, we actually know the area of all of the lawn and the area of all of the brick, which means we know the area of this whole entire rectangle that I'm outlining right now in yellow, right? So I'm going to use that overall rectangle to kind of try to model what's going on right here. So since that overall rectangle has brick area of 333, and then the lawn space, since it has dimensions 12 and 16, 12 times 16 gives you an area of 192, then if I put 192 square meters together with 333 square meters, we know that the overall area would be 333 plus 192, which gives you 525 total area. So we know that we can get area for that overall rectangle if we take its length plus its width and put that all together, right? So I'm going to just kind of erase some of this stuff right here. So if I figure out what the overall length of this is, right? So we actually know that from here to there, that's actually 16 meters, right? And then we actually know as well that that's an additional W, and down here that's an additional W, and if you put those three things added together, that's going to equal what this length is for the overall rectangle, right? So that means 16 plus W, which is 16 plus 2W is the length, right? So if I want to take length and I multiply it with width, I can put in the expression of 16 plus 2W for the length. So in a similar regard, if I find the width, which we already know part of it is 12, but then we know there's an additional W and an additional W that gets added in to make this overall width right here, then we would have an expression that is 2Ws plus 12, right, for the width. So therefore, 12 plus 2W gives you an expression for that overall rectangle, right? So this is a valid model for us, right? That total combined area of 525 square meters is the result of that length and that width times, right? So we can use this to solve and hopefully find the value of W that's going to make this true, right? So there's a little bit of foiling that we can do right here. We can do 16 times 12, which will give you 192. And then 16 times 2W gives you 32W. And 2W times 12 gives you 24W. And then 2W times 2W gives you 4W squared. And that's going to be equal to 525. All right, so with this, let's get everything all on one side so we get a 0 on one side. So I'm going to have to subtract the 525 over on both sides. So you're going to end up getting then a negative 333 from that. You also have your 4W squared, and then you're able to combine those couple of terms together with one another, which will give you plus 56W. All right, so if you could figure out a way to factor that or complete the square, you can. I'm just going to use quadratic formula to try to solve this. So we know then that W is going to equal plus negative of B, and then plus or minus the square root of B squared minus 4AC, plugging that all over 2 times A. All right, so we're going to get negative 56 right there, and then there's an 8 on the bottom since you have the 2 times 4, so negative 56 over 8, plus or minus the square root of whatever we get inside the root over 8. So yeah, let me figure out some of that stuff inside the root. 56 squared is 3136. And then if I do 4 times 333, that's going to be equal to 5328. Because there's a negative times a positive times a negative, you're going to end up plussing that. So yeah, if you add those couple numbers underneath the roots, we end up getting 8464 underneath the root. That's over 8. And then negative 56 is actually divisible by 8. Let's just get negative 7. If I square root the 8464, it turns out that we get a very nice number because 8464 is a perfect square. So we actually just get 92 over 8. And then if you do 92 divided by 8, you get a decimal number, pretty decent decimal number of 11.5 when you do 92 divided by 8. So yeah, negative 7 plus 11.5 or minus 11.5 would be your two solutions. So if you plussed negative 7 plus 11.5 would give you an answer of 4.5 for W. And then if you minused negative 7 minus 11.5 would give you negative 18.5 for W. So since W was representing that width of the pedestrian path, the negative 18.5 wouldn't make sense in the situation, right? It's just a solution to the equation, but doesn't really actually work, right? So 4.5 would actually work in terms of a length that would actually make sense, right? So that does tell us then that we'd have to make that width of the path be equal to 4.5 meters all the way around. And that really does answer the question because that was all that was asked of us here is just what's the greatest possible width of the path. So 4.5 meters.